Oh, I don't know what that's... Oh, a three-way valve then. This is a three-way valve, just showing you that the castings are identical. Now, moving on to another type of valve. This is a knife gate valve. It's another sliding stem valve, but this time it's a shut-off valve. So the knife gate valve, we tend to use it for shut-off, rather than trying to modulate a flow. We just have the flow on or off. The knife gate valve was designed for the pulp and paper industry. So it was designed to be, well, it was designed for them. They had specific requirements. They needed a valve that when you shut down, there wouldn't be any hang-ups. There wouldn't be anything left over. So with a knife gate valve, after you shut down, if there's any stuff on either side of the valve, you can quite easily, if you've got stuff hanging around here, you can quite easily clean it off with a hose pipe. So a knife gate valve is designed to be nice and clean. It's used by the pulp and paper industry. It's also widely taken up by the food industry. For the same reason, you can't have any hang-ups. Now, along came the mining industry and they said, oh, that would be just fine for our slurries. And they started using knife gate valves. Unfortunately, as rugged as it is for pulp and paper, they tend to have, well, they tend to be sort of knackered by mining. Here's some of the important things about the knife gate valve. Firstly, I like to call it, let me just go back, I like to call it a knife gate valve to remind people of what it is. What you've got here is a knife. The thing is a guillotine. When you've got a guillotine, and if you've got a big fat actuator like this one on the top, if that actuator shuts, or decides to shut, it's going to shut. If you've got your foot in there, it doesn't really care. It's just going to chop it off. So you never, ever stick anything of your body into there. I don't know what that's a drawing of. I suppose I could make it a shoe just to keep it decent. So you never stick anything into the knife part, because if the actuator decides to come down, it's coming down. It's got this lovely guillotine blade at the end, and interestingly enough, some mineral sands applications can actually sharpen this blade up until you get a razor sharp blade. So that's another thing to be aware of. It can be actually very sharp in there. Now, it's critical that the thing get put in the right direction, because the way, this is the blade here, I'm going to get a highlighter, that might be good. The blade is this bit, and the blade needs to push against the seal, the seat there, and there's also a seat there. If you plumb it in the wrong way, and people do that all the time, then what happens is that mineral sands get into here. I mean, they tend to anyway, but stuff builds up here and builds up here and gets up into the top seat and ends up breaking through the seal at the top. And yeah, well, it tends to make the whole thing seize up. There are serious problems with mineral sands and knife gate valves. The mineral sands were coming through and they were just eating away the metalwork. To try and fix this problem up, what they did is, I'll get a better colour than that, they put cones in. And what the cone is supposed to do is the cone is supposed to take the flow and direct it into the middle part of the opening so that it doesn't eat away the rest of the valve. So you have these cones. They're made of various materials, from plastic to steel. The idea of the cone is it's supposed to be a sacrificial item. And what you're supposed to do is every couple of months or so, you're supposed to open it up and replace the cone. That way, the valve body lasts forever. What actually seems to happen is that people wait. People say, oh yeah, with a cone, instead of lasting 3 months, the valve lasts 6 months. So they wait for the 6 months to be up, and then they change the valve. By which time the cone is completely gone, that's history, and so is most of the valve body. And then these valves in many mine sites are just treated as consumables. They're just thrown away and a new one put in. The cones can have different openings, and by having different shaped openings, you can actually try to control flow with them. You can actually try to modulate flow with these different types of openings. How well it works, I'm not exactly sure. Now, here's the butterfly valve. The butterfly valve is a rotary stem, and it's a modulating. So that means we can control flow. We used to have this rule that up to 300 mil, we would use globe. So we'd use a globe valve. But over 300 mil, we would use a butterfly. That was the rule we always used to have. And the reasoning behind it went along the lines of 300 millimeter globe would cost maybe about $30,000, whereas a 300 millimeter butterfly would cost $2,000. So even though a butterfly valve is not very good at controlling, a butterfly valve has absolutely horrible flow characteristics. You know, for the last 30% of the butterfly movement, it doesn't actually do any control at all. Even though a butterfly valve has terrible control characteristics, we would still buy it because it was cheap. So we would use butterfly valves all the time whenever we got big. Now, the problem that butterflies have is not so much that they have bad control characteristics. The problems that butterfly have is this piece of rubber here where they seat. This piece of rubber is called an elastoma. There's the problem. When the butterfly valve gets seated, it likes to stay there. Here I'm going to draw a butterfly valve, cross-section of a butterfly valve, and the butterfly is there. When the butterfly valve is seated, it's pressing into the elastoma really, really well. Now we come along with PID control, and PID control, we say the PID control, we'd like, I don't know, 30% flow, please. So the PID control says, oh, okay, 30% flow. Well, to get 30% flow out of a butterfly, I need to open it about, let's say, 20% open. So, the actuator comes along, and it's a big, fat actuator. It has to be a very, very strong actuator, because it's got to be able to wrench the butterfly disc out of the elastoma. So this big, strong, fat actuator comes along, and it tries to twist the butterfly valve to 20% open. But the butterfly valve doesn't move because it's seated. It just stays there. It just stays nicely in its seat. And instead, all that happens is the shaft corkscrews up. So the shaft just rotates around and torsions up. So, no opening, no flow. So PID says, oh, that's no good. I need to have that valve open. So it opens the valve 21%. Still nothing. So it says 22%. Nothing. 23%. Nothing. 24%. Still no good. And it keeps trying to open that valve until it gets to about, say, 30%. And then the valve says, okay, well, sod you, I'll open then. Now, it doesn't open nicely and slowly and gently. What it does instead is it goes bang! Opens 30%. Pretty well at 30%, a butterfly valve is a fair proportion of the flow. So the flow goes from nothing to virtually full flow in 0 time. Remember, most butterflies are over 300 mil. So a very large valve just banged open in 0 time. Now I'm sure you know how much noise it makes when when the solenoid opens and closes on your dishwasher at home or the washing machine at home, and that's on a 15 mil pipe. This is a 300 mil pipe that just banged open full bore. Every piece of pipework in the factory is now going bang, rocking backwards and forwards and shaking. That's a bad thing. Has anybody got any experience with butterflies? Have you ever seen them get stuck in their elastomer? Now, in some places, they actually have 2 butterfly valves for every butterfly valve they need. One is off in the factory getting a new elastomer fitted. Because sometimes, when the butterfly valve comes, when it opens and pulls itself out of its elastomer, it also gets hold of the elastomer, wrenches it off its casting, and throws the entire elastomer down the pipeline somewhere. You'll find it'll be stuck in the pump impeller. So that's where you'll find the elastomer. It'll wrench the whole bloody thing off its seat. Changing an elastomer is an absolute nightmare. It's a horrible job, tire irons and big rubber mallets. I really don't got a lot of time for butterfly valves. One solution is, if at all possible, try to not let the butterfly valve close for a long period of time. If it's possible to do so, just keep the butterfly, say, 5% open at all times. I mean, and then it won't stick. The problem with this is that you get this very small leakage rate through the butterfly, and that will lead to a few problems with what's called cavitation and flashing. We're going to talk about those later. So that can be a problem with butterflies when they're just slightly open. Here's a cross-sectional drawing of a butterfly. You can see there's really not much to it. It's very cheap and cheerful. Now, a few years back, we got better at making metal. Specifically, we got much better at making balls. We got really good at making balls. So we started making ball valves. Here's a ball valve. Have you all had experience with ball valves? Have you all seen ball valves? That's good. Now, one thing to bear in mind about a ball valve is you don't need the entire ball. In fact, you only need kind of half of the ball, really. Providing you've still got some way of moving that ball around, you only need the half a ball. So you can get ball valves. This ball valve This one here, that's just a half-inch ball valve, so that's a 15mm ball valve. 15mm. This other one here, that's a 400mm diameter ball valve. We're very good at making balls nowadays. We can make balls as big as you like. Now, ball valves were initially made purely for shut-off duty. They were only shut-off valves. And then somebody had the crazy idea of sticking an actuator on the top of the ball valve. Here's some other pictures of ball valves. So someone had this crazy idea of sitting an actuator on the top of that and actually modulating using a ball valve. Here's some different balls to show you only need half of the ball. When they started modulating using the ball valve, they found that a ball valve was quite a nice control valve. It did have some problems when it was first opening. So when the ball is initially opening, the flow wasn't very pretty, because when the ball would initially open, if you imagine that that's the hole, then the shape of the shape that would be exposed would be like a moon shape, like that, like a crescent shape, and that wasn't very good at controlling. So what they discovered was they could get much better control if they cut a V shape on the leading and trailing edges of the ball. See the V on these balls? And they're called V-balls. V-ball, strangely enough, because it's a ball with a V on it. Now, V-ball valves control much nicer. They have nice control when the flow first starts, and they control nicely over their range. Interesting things about a ball valve. When a butterfly is almost fully closed, the flow is being directed all down to this point. So all of the force, all of the hydrodynamic force is on this part of the butterfly. Draw that butterfly there, come on. What that means is you have to have a really strong actuator to get it shut. Then, once it gets sat in its elastomer, you need to have a really strong actuator to get it out of its elastomer. So it's hard to open and close a butterfly. With a ball valve, on the other hand, what happens is the flow gets directed into the casting. And the way that the ball is cutting the flow is this bit of the ball here comes upwards and cuts the flow, almost like a knife gate. It cuts across the flow rather than fighting the flow. So a ball valve doesn't mess the flow up as much, and it's not so hard to close it. You only need a smaller actuator. That and the fact that it's not going to get caught in its elastomer because it doesn't have an elastomer. These are different types of ball valves. Now, these are actually some different types of butterflies, which the butterfly people realized the big problems they had was the fact that the butterfly blade and the axes were in the same axle. Yeah. So what they discovered was that if they offset the butterfly blade, they wouldn't get so many problems with sticking. So you get these things called offset butterflies. In fact, the very best butterfly valves have got the blade very, very offset like that. This is the ideal butterfly. Now, can anybody see what that actually is? Yeah, you're right. the ideal butterfly is actually a ball valve. So, we've got to this really weird situation where we now have a modulating ball valve that controls much better than a butterfly. It needs a smaller actuator, size for size than a butterfly. It doesn't stick like a butterfly does. It doesn't rip its elastomer out like a butterfly does. And, well, it's a better valve. But we don't use it that much. And the reason we don't use it is because of tradition. Tradition says greater than 300 millimeters, we use a butterfly. And it takes a lot to change stupid traditions like this. It's a stupid tradition. We should use balls. Balls are much better at controlling. You get a lot less trouble with a ball valve than you would with a butterfly. Of course, there's always horses for courses. There's times when you must use a butterfly. But given the choice between a ball and a butterfly, I'm going to use a ball valve every time. Price-wise, if you were to say that a globe valve of any particular size, a globe valve would be 30,000, and a butterfly would be 2,000. A ball would be about 5,000. So they are much more expensive, well, more than twice the price of the equivalent butterfly, generally speaking, and I'm generalizing it, but it's money worth paying.